We'd proceed in the vector field and then path independence and path dependence. Path independence and path dependence in vector field. So these are the areas they not only provide a kind of different concept, but they also provide a alternative way to do the actual line integral. So that is the scenario. If I want line integral of a vector field, if I have a vector field and if I want line integral of a vector field along a particular line curve, if I have a vector field capital F is vector field, small f is algebraic function. So there are two things. Both are algebraic. Vector has a vector has a nomenclature where it has first component, second component, third component, fourth component, and nth component. So if it is three-dimensional vector in Cartesian coordinate, then it has x component, y component, and z component. Okay. If it is a static vector, then all three components are scalars. Whereas if it is an algebraic vector or vector field, then all three components are function over the independent variable. So if independent variable is x, y, and z, then it is the first component is function over x, y, and z. Second component is function over x, y, and z, and third function is function over x, y, and z. If they are function over x, y, z, so we can call it like if capital F is a vector field, then capital F bracket x, y, z, because three are independent component. On top there is an arrow. It's a vector, and that is f small f f x y z I plus g x y z j plus h x y z k. So this is also called algebraic vector field. What about if I have a vector where the independent component is only one, that is t. So if there is a vector, then there are components. Suppose there are three components. Okay, first component, second component, and third component. First component is function over t. Second component is function over t, and third component is function over t. Then this kind of algebraic, this is also an algebraic vector, is represented through small r in braces t because there is one independent component t. If that is the case, then it is called parametric vector. So difference between parametric vector and vector field is function over the Cartesian coordinates, typically x, y, z, whereas the whereas the parametric vector must be a algebraic vector over single independent component, that is small t. Okay, now we come to stage that if I have algebraic vector capital F and I want line integral of the capital F. Line integral, everything is line integral only. Integration means line integral. Integration means if I have a function, and if that function I want to calculate integration over dx, then function is nothing but vertical component. Many times I have kind of spoken about it. So if there is a x component and there is a function over x, then for fx, that is the vertical component. At each x, fx is different. If it is constant, vertical is constant at each x, then quickly I can find the area of the rectangle, and that is the integral. So integral is nothing but height into width. That is the integration. So integral is always line integral. Integral in the sense whatever is the fx multiplied by the length of the line. Length of the line. If that is the case, then all integration are line integral only. But the vector field line integration is instead of fx being an algebraic function, we have a vector field. So now if I have a x-axis and then I had algebraic equation, instead of algebraic equation fx, now I have vector field. Vector field have I component, j component and k component. Means in Cartesian vector field. Now, what is this vector field integration along dx? If it is fx, then fx dx integration. That is nothing but fx is the height and dx is the length. Height into length is the line integral. But what about the line integral of vector field f? Means what we want, vector field f is capital F and then above one arrow sign. That is the vector field. Capital F dot dx vector. That is the line integral here. There it is fx dx. Now here fx dx with small f. Here capital F dot dx vector. Capital F vector dx vector. Why it is? So we have talked much detail about it. Why it is in a sense that if I have a vector field like this, if there is a vector like this, and this is x-axis, this is x-axis, and there is a vector like this, then if I want to calculate the kind of the this vector field's line integral along this axis, then this vector field has two components typically. One component along x-axis and one component along y-axis. So if this is a vector, then y-axis component, and this is the vector, then x-axis component. If that is true, then first we have to find this vector along the x-axis. If I find the vector along the x-axis, that is nothing but this vector dot product with the unit vector along x-axis, that is I. If I do so, then it turns up into an algebraic equation. Capital F array equal to F1 array, F1 vector I plus F2 vector J plus F3 vector K plus F4 vector whatever. All its component along with its unit vector, all is vector field capital F, where F1 vector is algebraic equation over independent component x, y, z, whatever. F2 is again algebraic equation. F3 is again algebraic equation. Integration always happens on algebra, not on vector. Okay. So if I say capital F dot dx, then now I'll talk about both. One, I'll talk about this mathematical way, and one is what actually is happening. Then capital F dot dx vector. If it is x vector, then I can take out the, it is nothing but, any vector is nothing but magnitude into its direction. So x vector, I can just say I x, I vector x. Instead of x vector, I can say I, that is I x is I vector x. If I take it out, then it becomes f dot I vector dx. F dot I vector is the, if it is x-axis, then that is the first component. First component is algebraic equation, that is F1. So capital F vector dot I vector is nothing but F1. F1 is algebraic equation. So F1 dx. So at the end, we have to come to algebraic equation dx1. But so this is line integration. Line integration means that line integration of a vector. Now, if this is x-axis, consider this is u vector. Instead of x-axis, it is u-axis, u vector. If it is u vector, then integration of this vector field capital F along u vector, earlier we calculated for I vector, then capital F dot du vector. That is nothing but u unit vector into u. U unit, then earlier it was I dot I into x. Now use unit vector into u. Unit vector, if we take it out, then capital F vector dot unit vector of u du. So that is not F1 or F2 or F3, because unit vector of u, will be in terms of I, J and K. Whereas the capital F is again in terms of I, J and K, F1, F2, F3. If I do dot product, then at the end it will result into an algebraic equation. So that algebraic equation du, that is the kind of line integral. So line integral of an algebraic equation along a particular direction. So if I have algebraic equation, I consider that as height, then particular direction means multiply by that. But that height is not constant. Every point the height is different. That's why calculus is there. If height is constant, then height into width is the area. Area is the end that we want to calculate through integration. Integration is a form of addition where addition is calculated through calculating the area. So if I have height, but height is varying everywhere, then I cannot take a single height into width. If someone gives me average height, then it is fine. I don't need calculus. Otherwise, then calculus comes into the picture. Please watch earlier. We have from the bits and pieces from neutron, proton, electron till the higher level, everything we have talked, that how mathematics evolved, and then how integration evolved, how differentiation evolved, and then what we try to do. Now, if I have line integral of vector field f, but that is nothing but vector field f along that axis on which I am trying to calculate the line integral, so that with dot of that unit. So if I go this way, not through mathematics way, then if I have vector field f and this is any vector u, then f component along u, first that I have to calculate so that they will come along each other. If they come along each other, then only whatever algebraic equation I am getting, that is the vertical component. That is the main thing. So if I have capital vector F, then capital, if this is F, then component along U is F dot product with the unit vector along U. If that I get, then du like dx. Same thing what we did now. Capital vector F dot du vector, unit vector, I took it out and then I saw that it is dot product, or we understand through the spatial way or through the kind of 3D understanding. So both will come to same location. Now idea is that I have to calculate line vector, line integral of a vector field along a particular line curve. If there is a line, if this is the line, if this is the line curve, if this is the line curve and this is the vector field, I have to calculate integration, then this is beginning point and this is end point. So beginning point to end point, I have to calculate the line integral along this direction. Can you see this? I was talking about u as vector along the u vector. The u vector is also a vector field. It is algebraic vector. Algebraic vector. It is not a straight line. Vector field f, line integral along u vector. U vector is also curve. And vector field f is, since it is algebraic equation, at each point of the curve, this vector field is also changing because algebraic equation. Whereas line curve is also algebraic equation. Both are vector field. Whatever. It is capital F dot du vector integration from the beginning point to end point. Okay. Now, but it became like if you kind of find a solution, if you find the solution, I don't know how to enjoy kite, right? Means you have a thread and then you pull up the kite in the sky and then you enjoy kind of playing with the kite. So that is an art. I don't know. I mean, I know. I am saying I don't know. So I don't know how to kind of play the game of kite. Now, slowly, I learned that you have to first prepare the kite or go and buy from the market and thread, and then you have to do like this or through whatever you kind of wind up, roll up the thread in some kind of roller, small roller, then through that you can play with the kite. I knew it. What is the next step? Now I'll try to refine it. because there is a war happens in the sky for the kite, at least in India. Means your thread should be kind of, it should be uh, coated with some material that if falls on other kite's thread, then it should cut it down. These are kite games that happens in India. So then once you know that how to kind of and how to play with the kite, that game you understood, then next step is that now you will think that I have to kind of do some efficient way to play with the kite so that your kite should not go down because other people would cut it. So day by day, you will start doing refinement. First, you were thinking that somehow I have to understand the game of kite. But slowly, you will start doing the refinement in it. So earlier, the main game was that how I can calculate the vector field line integral. If I have a vector field where vector is algebraic equation, it keeps changing at x and y, x point, comma y, then line curve is a vector. Then slowly they saw that line along which they are calculating the line vector. It is not a vector, it is also a variation among the x and y. Now they have found out it is nothing but capital F, that is the vector field, dot d u vector, integration from beginning point to end point. If they understood people, now they are looking for the refinement further. Okay. Now, further, what can we do now? So, people, what they saw is if I have capital F dot du vector, if I do integration and from lower limit to higher limit, then it results, the net result, if I don't place the limit, if I don't place the limit, only capital F dot du. So if there is a u vector, then any u vector, I can I can address it through position vector, that is xi plus yj. If it is a vector field, then xi plus yj, any xi plus yj. If that is true, then du vector is nothing but dxi plus dyj. Now I have a vector field that is f1i plus f2 capital F, f1i plus f2j. f1i plus f2j dot dxi plus dyj, that turns up as f1 dx plus f2 dy. So now f1 dx is algebra, f2 dy is an algebra. Altogether, if I do the integration, it results in an algebra. If it results in an algebra, consider that that is called potential function. If that is potential function small f, if that is potential function small f, then what is relationship of a small f with whole integral, that is f dot du vector? If that relationship, if I do refinement, more refinement, then what people saw is a small f. If I do df by dxi, means if I do partial derivation, it turns up into a vector called gradient vector. So df by dxi plus df by dyj, df by dxi plus df by dyj, that results in gradient vector. That gradient vector is nothing but the vector field. Okay, amazing, man. Means if I receive one algebraic equation small f after doing the integral without calculating the limit, f dot du vector, capital F vector dot du vector, that turns up as f1 dx plus f2 dy, then if I calculate this, that results in an algebraic function. That algebraic function is small f, then df small f, df by dxi plus df by dyj, because it's a gradient vector at the end if I do partial derivative. That vector df by dx I plus df by dyj, df by dx small f, df by dx is nothing but first component of the vector field capital F, f1. So f1 equal to df by dx, f2 equal to df by dy. For proof, please watch the last session. So we did kind of thorough proof in two ways for this. Now people saw that vector field capital F is nothing but gradient vector of a algebraic equation F. If that is true, if that is true, then if F1 is df by dx, small f, dfy by dx, and F2, that is vector field capital F, F2, F2 is df by dy, whereas f is small df by dy, then what we are getting here in line integral? F1 dx plus F2 dy, F1 dx plus F2 dy. Okay, if we replace with this gradient vector, then it results in single f df by dx into dx, f df by dy into dx, df by dy, that is f2 into dy, mean dy, f. So the line integral f vector field f capital F dot du turns up into small f, that is algebraic equation that I am receiving through line vector. So the algebraic equation I am receiving through line vector computation, that algebraic equation small f, if df by dx is f1 and df by dy is f2, then there is only relationship between the result with with the vector field. There is no relationship with the u vector at all. This is what was seen. Okay. If that is true, then end result, that is small f, is only related to the capital F, not on the dot du. If that is true, then it is called path independent. Path independent in the sense when u is gone, du is gone, u is the line curve, the curve on which I am calculating the line integral. If this is the curve, then on curve I am calculating the line integral of vector field capital F. If this part is gone, it is not dependent upon this. The end result is only dependent upon the vector field. Then it is called path independent. When path is not there, then it is path independent. If it is path independent, then capital F vector dot du vector, okay, that is nothing but algebraic equation small f. Small f integral a to b, lower first point of the line curve and last point of the line curve. So f is algebraic equation. Now place the higher limit minus the lower limit. If that is the case, then it is path independent. If it is path independent, then if I am calculating the line integral along a path where there is a begin and end, then this path is of no importance. Either it is a straight line, it is a circular, or it is a parabola, or any equation. Only begin point and end point matters. That's it. If I know capital F has a is related to a function where that function's gradient vector is capital F, if that is true. So what is required here? The requirement here is I have to find a algebraic equation small f for which gradient vector is equal to the vector field capital F. That function is required. If that function I am able to find in the space, then I can say this is path independent. If this is path independent, then life is just like a cotton, means it is so smooth now. Now, if you know one end, if you know other end, and you have to calculate line vector, then it is a parabola. Any complex equation of the line doesn't matter. Only begin point, end point, and vector. And then your line integration is done. This is the big refinement. I don't know who did it, but God has given extra brain to that person. That is guaranteed. Okay, that is guaranteed. So if that is true, then we have idea just to find the algebraic function for which the gradient vector is the vector. Now consider that there is the vector field is y sin x, y sin x I is x-axis vector, y sin x I plus y plus sin x j. This is the vector field. Y sin x I plus in bracket sin x plus y bracket close j. If this is the vector field. For this vector field, if there any exists a algebraic function for which this vector field is the gradient, that is the idea. For the, if I calculate the gradient of that algebraic field, then this that would result in this vector field y sin x I plus y plus sin x j. If that is true, then the first component of the vector field, that is f1 equal to df by dx, f2 equal to df by dy. It is not up to here only, it is much detailed. We have discussed in the last session. So df, now if I have f1 equal to df by dx, where f1 is capital vector field first component and df by dx is the small f, that is algebraic equation that we are eyeing to find out what is f. So df by dx equal to f1. Here f1 is y sin x. So df by dx equal to f1. So algebraic equation f is integration of y sin x dx. If that is true, then it results in minus y cos x. The integration of y sin x would result in minus y cos x, minus y cos x plus any function c over independent component y. Means any algebraic equation which has only y, minus y cos x plus any set of algebraic polynomial equation only in y. If that is true, then we have algebraic equation f, small f, equal to minus y cos x plus all y. If I do again df by dx, then it would result in y sin x plus 0. So this is what is the df. If df by dx is f1, capital F1, then the algebraic equation what we are looking for, f is nothing but minus y cos x plus c is any function c over y. Now we got the f. Now df by dy is f2. df by dx is f1, capital F1. Then df, where f is small, df by dy is capital F2. So through first equation, I got the small f, algebraic equation, that is minus y cos x plus any function c over y. Now I'll differentiate with the y, df by dy. That would, if I differentiate it minus y cos x, then it would result in minus y minus cos x. It would result in minus cos x minus cos x. If it results in minus cos x plus the dc, c is a function, then dc by dy, dc by dy. Now df by dy is y plus sin x. Okay, so y plus sin x equal to minus cos x plus dc by dy. Okay, so I have done something wrong here, because here something wrong. So I'll rephrase the problem. So vector field capital F equal to y plus sin x, y sin x I plus y plus sin x j. Now I am making it y cos x I, y cos x I plus y plus sin x j. If that is true, then df by dx equal to y cos x. If that is true, then small f equal to y sin x plus any function c over y. Now the algebraic function what we are looking, the small f equal to y sin x. We know now we have taken y cos x I plus y plus sin x j. Now it turns into df by dx equal to f1, that is y cos x. So f, small f equal to y sin x plus any function over y, c. Now if function, what we are looking for, the algebraic function small f equal to y sin x. Okay, so we had taken y cos x, it result into y sin x, y sin x plus any function c of y. Now if I do df by dy, then it will become sin x. Sin x plus dc by dy, where dc by dy is any function over y. Here df by dy is nothing but sin x plus y. The vector field capital F is y cos xi plus y plus sin xj. So the F2 is y plus sin x. df by dy is nothing but F2. So y plus sin x equal to sin x plus dc by dy, where c is any function of y. If that is true, then sin x cut down, and now dc by dy equal to y. So the c equal to y square by 2. If c equal to y square by 2, then earlier we had calculated the algebraic function f equal to algebraic function small f equal to y sin x plus cy. Cy I got as y square by 2. So y sin x plus y square by 2 is the algebraic function we are looking for. So gradient is available. Means the algebraic function is available for vector field y cos xi plus y plus sin xj. If I am able to find the algebraic function around the globe for a vector field y cos xi plus y plus sin xj, then that vector field is called path independent. Means I got the lottery. Means lottery is in my name. If that is true, then vector field is path independent. If that is true, then vector field f along any line path, that is u capital F dot du vector, limit a to b, now inside it completely change into algebraic equation f. Now f is y sin x plus y square by 2. Just keep it and place the limit a to b. What is the actual, if there is two end of the line vector, what is the, it is a line, it is parabola, doesn't matter. With capital F, I calculated the algebraic equation of small f that turns up as y sin x plus y square by 2. Then y sin x plus y square by 2, limit a to b. Any number you place, whatever the value you get, that is the line integral. So this is path independent. Okay, but not all vector would be path independent. Let's take algebraic vector capital F. Algebraic vector means vector field capital F equal to 2xyi plus xyj. 2xy, 2 into x into y, 2xyi plus xyj. If that is capital F, then F1, the capital F1 is 2xy and capital F2 is xy. Now I have df, where f is small, that is the result. df by dx is f1. If df by dx is f1, then the algebraic equation of small f is f1 dx. 2xy dx is 2x square, 2x square by 2 means x square y plus any function over of y, that is capital Cy, I can say capital C in bracket y. Capital C is a function of y, function over y. If I have small f, that is the algebraic function small f equal to x square y plus any function over y. If I do again df by dx, then it will turn up as 2xy plus right side over. This is what we had earlier. Okay. So now we know that algebraic equation small f is now x square y plus any function over the cy. Now df by dy, if I calculate df by dy, that is f2, then df by dy equal to x square. It was earlier x square y. Now it is x square. X square plus any function of y1. Here df by dy is xy. Because if you remember, the vector field we have taken is 2xyi plus xyj. So df by dy I can replace with the f2, that is xy. So xy equal to x square plus dc by dy. So dc by dy is xy minus x square. Xy minus x square, if I integrate with the dy, certainly there will be x term, whereas this function must not have x term, only y. That is required. So if I have algebraic equation small f, so small f, so df by dx equal to f1, capital F f1, then f equal to capital F1 dx, capital F1 dx plus any function over y, so that df by dx would result in f1 and 0. But here I am getting, that is, if I call it cy, then cy I am getting as a function of x and y. It should be only function of y1. So there is no algebraic function of small f exist whose gradient will be the vector field. If vector field is 2xy I plus xyj. So not all vector field has a algebraic function small f which is whose gradient is capital, means for every vector field capital F, there is no requirement that there is no compulsion that there will be algebraic function small f exist. If that is the case, then this is not path independent. This is path dependent. If it is path dependent, then your life is gone. Life is gone in the sense that if you have a vector field 2xyi plus xyj, and you have to calculate line integral from point A and to point B, then how the line is, that matters now. It is a semicircle, it is a parabolic, it is a straight line, it is convex, concave, whatever. If there is a 1000 line algebraic equation from point A to B, then 1000 times you have to calculate the line integral if it is not the path independent. How it is not path independent? Because capital F, for capital F in the world, there do not exist a algebraic function small f. Okay, if I equivalent of capital F, there do not exist any algebraic equation that is small f. Okay, whatever algebraic equation exists, if I calculate the gradient vector of those algebraic equations, they are not equal to capital F. If I have algebraic equation for which gradient vector is equal to capital F, then I found it, but it's not possible. So not all algebraic equation, not all algebraic vectors are path independent. So this is the case that we are not able to find algebraic function for a algebraic vector, if we are not able to find algebraic function, then this is path dependent. Why we go with the f1 equal to df by dx? F is small, then df by dx. I have talked nicely that if I see the line vector, that is f, capital F dot du vector, where u is the line, capital F vector field dot du vector. Okay, any vector field can be represented as position vector xi plus yj. Du vector, that will result in dxi plus dyj, whereas capital F vector field will be represented as f1i plus f2j if it is two dimensional. Now, if I do dot product, it will become f1 dx plus f2 dy. If that is true, f1 dx plus f2 dy, this is nothing but small f, that is the algebraic equation. If that is true, that f1 dx plus f2 dy is the small vector, then to make it exact representation in the, then f1 dx equal to, if I say f, then f1 would become f df by dx. If f2 dy is f, then f2 becomes df by dy, whereas f is small. In this fashion also. Okay, since their integration is the algebraic equation, then algebraic equation differentiation is the algebra. if I have algebraic equation whose integral is a algebraic equation, this algebraic equation differentiation is this algebraic equation. Reverse is true. So we can say that the capital F, that is the vector field, capital F is nothing but the gradient vector of the net algebraic equation we had calculated, df by dxi plus df by dy, where f is small, that is nothing but the vector field capital F. But df, the algebraic equation F, finding is difficult. If you are able to find it, then it is considered as the vector field capital F is considered as the line vector, considered as the path independent vector. Okay, one more example that we had kind of assignment, or we can say questionnaire we had given, that Earth, there is a Earth, and Earth pulls anything. Earth has gravitational pulling force. So if there is a Earth and there is a mass at distance r, then Earth pulls the r towards it. Then this vector, we call it minus, because Earth pulls it. If it is in this direction, so from Earth it is plus. But if this is Earth and it pulls towards its center, then it is minus. Now, what is the pulling force of the Earth? That is minus k r vector divided by r square. This is what we had said. K can be a constant. Typically, I believe gravitational force into the kind of mass of Earth or whatever. So minus k r vector divided by r square. R vector is nothing but the vector. If this is the mass and this is Earth, then mass and Earth center. If I draw a vector, that is r vector. So minus k r vector divided by r square. So I am not going to the Earth center. Earth surface is also okay, but direction should be towards the Earth center. So that is r. Now prove it that this is path independent. If it is path independent, then this is a vector field. Capital F equal to minus k r vector divided by r cube, not r square, r cube. If this is, then I have to find an algebraic equation whose gradient is this vector. Okay, if that is true, then this vector's integration, if this vector's integration is the algebraic equation. So since it is small r is the vector, then like if I want to find so if I consider this as a spherical coordinate, then I need not find x and y component. Consider r as a one of the orthogonal component in the spherical vector, radius vector. If that is true, then we will find the algebraic equation of this vector field. If this is the vector field, and if I have to prove it is path independent or not, for this vector field f, capital F, there should exist one algebraic equation small f, okay, for which the gradient vector is this capital vector f. So what is f is minus k r vector divided by r to the power 3. Now r vector, I can say r unit vector into r unit vector into r. Then it comes as it comes as minus k r unit vector divided by r square. Okay. Now this I have to integrate with the dr. Okay, that is the idea to get the algebraic function. Now I can remove the direction, because I am getting now there is only r, there is no dot or cross product. So there is only r unit vector. So only the magnitude what it is, it has. The magnitude is minus k by r square. Minus k by r square is the magnitude. dr is the small potential function of small. What is the integration of 1 by r square? The integration of 1 by r square is 1 by r. 1 by r differentiation, if I see r to the power minus 1, will become minus 1 by r square. So minus k by r square, the integration would be k by r. So k by r is a potential function, small f. We found it. So if potential function is small f is k by r, then gradient vector of the k by r, if I calculate, then it becomes minus k by r square and then r unit vector. This is what we are looking. If I replace r unit vector with the r, then minus k r vector divided by r cube. That is the vector field. So the potential function small f exists. If it exists, then this proves that the gravitational pull or force of the earth is path independent. If it is path independent, then if there is a mass, so if it is here, then it contains energy called potential energy. It contains one energy, potential energy, and if I drop the mass and it hits the ground and stand there, how much energy it lost, or how much is the work done by the earth to pull it from here to here. Both is same thing. Either it loses the energy from here to there, or earth done some work to get it pull pull it from here to here. How much energy that is involved? That is same as if this mass, rather than dropping it, I take one slope slant and place there and slowly it goes down, or I keep it on a stair and dip it goes and hit the ground. Okay, it does the same work. Earth gravitational pull does the same work. Either it goes by the stair, means it takes different path from the begin to end, or I drop it. Okay, for earth doesn't matter, it does the same work, because earth gravitational pull is path independent. If it is path independent, then it does the same thing. Now we can do more on it, like we calculated algebraic function as k by r. If it is k by r, if I convert into Cartesian coordinate, it comes as k by square root of x square plus y square plus z. That is the radius. K by x square plus y square plus z square. Now if I do df, this is the algebraic equation small f. K by square root of x square plus y square plus z square. Now, if I do df by dxi, gradient vector, df by dxi, df by dyj, and df by dzk, trying to calculate the vector field, because vector field is minus k r vector divided by r to the power 3. It comes there or not. So, if I take Cartesian coordinate, if I take Cartesian coordinate, my k by square root of x square plus y square plus j square as the potential function is smaller, then df by dx, df by dy, and df by dz. If I add like df by dxi, df by dyj plus plus, and plus df by dzk, then this would result in a gradient vector. So what is the differentiation of 1 by k by square root of x square plus y square plus z square? That would result in, okay, if you calculate the differentiation, then that would result in minus x divided by x to the x square plus y square plus z square to the power 3 by 2. So if I keep adding, then it would result in a vector that is minus k and inside bracket xi plus yj plus zk divided by a square root of x square plus y square plus z square. This is what is the vector field capital F. So minus k and xi plus yj plus zk is the r vector divided by the magnitude x square plus y square plus z square to the power 3 by 2 is nothing but r to the power 3. So with the gradient vector in Cartesian coordinate also we get back the vector field, that is the earth. So these are the kind of milestone that has been achieved in calculus, the kind of pioneer thing, like in electronics, people are communicating to like Voyager. I believe that is the most marvelous thing that has happened in field of electronics. Voyager 1 and 2. So they kind of went much ahead of Pluto, and still they are able to send the signal. Means that much is developed the electronics communication signal system. Then calculus has come to this system, that we have now vector field and path independence and those kind of things. Few more things that we will see. But as we know that if I am making a building and if foundation stone is very powerful, then it is matter that how much I want building height, how much tall building I want to erect, that is up to me. So calculus, the base is so powerful that it can go to any extent, it will cross the universe to any extent what we want. So this much people have come to a strength. Now we will see kind of path dependence. We have talked everything about path independence. So in path independence, we have seen now if it is dependent upon begin and end. If begin and end are same, so it takes this path, this path, this path, this path, and come to same location back. Then the net line integral is nothing but potential function f limit lower to higher. The lower to higher is same. Then for path independent vector field, if it is begin and end is same called circular path, then line integral is zero, must be zero. If it is zero, then then another check that we can say that vector field f is path independent. If line integral of vector field f along a closed loop is zero, then also we can say that it is path independent. But someone has to calculate that much. Far easy to calculate the potential function, and then you can say if it exists, then it is path independent. If it is if closed line integration is not zero, abruptly you can that moment you can say that vector field is not path independent. No need to calculate the potential function. Or potential function is not coming as a well-defined function, then again it is not path independent. Okay, so if it is path dependent, then what are the another world? This is this world. Then what is another world when it is path dependent? That we will see.